Hi there, I'm Rob van der Goot and today I will be presenting my work on open challenges in language identification. So the task of language identification is to map a text into a language code. We commonly use the ISO standards for these language codes, which have their own issues, but for a practical perspective it makes sense. And people have shown very high performances with different types of models on different types of setups. So the question I'm asking here, are there still remaining challenges? And if yes, which ones of these are the most important? To answer this question, I want to do a systematic analysis of different setups. And to get to these different setups, I collected a variety of data sets that I all combine into the same format. And you can see them here on this slide. They were chosen to capture a variety of domains, scripts and languages. In my study I compare 5 different models, so these are picked on broad categories of models that are commonly used for this task, and here they are sorted by complexity. So we have n-gram overlap models for which we use TextCut, which compares character n-grams. We have machine learning models, here we use naive Bayes, which is very commonly used for this task. Then we have fast text and LSTM and language models, for which we pick GLOT 500 after a small comparison stage. GLOT 500 is trained on 500 languages, which is one of the widest coverages for as far as I know. You should note that the largest model here is 10,000 times as large as the smallest model, they're here sorted by number of weights, and there's a very large difference. So the first dimension I want to evaluate across is size. And to do that, I have 3 different types of size that I want to compare systematically. So I have the number of languages, the number of iterances in the input, and the number of characters in the input. So I make these dimensions match during training and testing time, although for testing I always use 1,000 utterances to get an accurate estimate of performance. And we can see the results on this slide. So on the y-axis here, we have the accuracy. And then we have these sets of bar plots grouped together, which are all different setups, and the different colors are the different models. So the first thing I would like to talk about is the number of languages. And that are the 3 different plots that we have on the y-axis here. So we have 10, 100 and 1,000 from left to right. And we can very clearly see that there is a small drop in performance if we increase the number of languages by 10-fold. But the drop is also small at the same time. So in the end, adding languages comes at a very small cost. So I'm mostly interested here in the 100 and 1,000 languages, so we get rid of the other one to get a more focused view of the results. Now let's talk about the number of utterances next. So we group these here on the y-axis. So we have 10, 100 and 1,000 utterances. And we can very clearly see that 10 is not enough. Performance is low for all models. But for 100 we already get very high performance, and for 1,000 we get a small increase again. I would hypothesize that for 10,000 we would get slightly higher performance, but this of course comes at the cost of coverage, because not for all languages we have 1,000 utterances in our datasets. So the practical takeaway here is that 1,000 is probably enough, and even with 100 we can already learn quite a lot. Now if we zoom in further and we remove the 10 utterances because of the low performance, we can next talk about the number of characters and the models. So the number of characters are here indicated within each bar, and we can very clearly see that 10 characters is not enough information, but with 100 we already get quite far, and then if you move to 1,000 you get only very small returns. So 100 characters is also usually enough. If you look across the different models, which are the colored bars here, we can see that all of them perform mostly on par, and the setup is more important than the model itself. Although there are differences within these that are still significant. So for example, the LSTM model underperforms here, which could also potentially have been alleviated by doing more hyperparameter tuning. But overall we see small gains from increasing model complexity. Now let's look at the families and scripts next. So to evaluate for these, I make different subsets of my dataset with a specific number of languages per family or per script. These are the results, and the trends actually show only a small impact. The impact for script is a bit larger than for family, and we get this very surprising U-shape here. I hypothesize that this is because we can learn more accurate representations when we get more data per script. So that's why the medium numbers lead to the lowest performance. Then if you move on to the domain dimension, we would evaluate our model across domains. We have here 3 source domains and 5 target domains. So the source domains are on the y-axis, the target domains are on the x-axis. And we picked these for practical reasons because of dataset size. For the 2 target-only domains, we don't have enough data. But we can very clearly see that in this diagonal we have the highest performance, and also when we train on the combined training set of all training sources, we also get highest performance. But we can very clearly see a large drop when we go cross-domain, especially to the completely unseen domains. Now, this is for the largest model, so the GLOT 500 model, it's a transformer-based encoder. But if we look at the other neural network models, we see a very, very similar trend with similar or even larger drops. Now, very, very surprisingly, we get much more robust results with the simpler models. So here are the results for naive Bayes and TextCut. And we can very clearly see that they perform much, much better across domains, indicating a higher robustness. Naive Bayes is clearly the winner in this experiment, but also TextCut does relatively well. So to sum up, a small number of utterances, around 1,000, is enough for accurate language classification. Family and script have only a small effect. The cross-domain dimension is the most challenging, although I would argue it's the most realistic setup, because in most cases we're not so interested in classifying Wikipedia or Bible data. Larger models do better in dataset, but small models are much more robust across dataset. So even the gains with larger models in dataset are relatively small, but across dataset the differences are much, much larger. We also release our final model with over 2,000 languages and have additional analysis and experiments in the paper, of course. Thank you for listening. Bye.